Today, I would like to introduce Protocol-Independent Multicast, or PIM, one of the most widely used multicast routing protocols in the industry. Today's course will help you understand the basic concepts of multicast routing protocols, as well as the usage scenarios, working mechanisms, and basic configurations of two types of PIM, PIM-dense mode and PIM-sparse mode. Let's start off with an overview of PIM. Before we begin, let's review the multicast routing architecture. It consists of three parts. The first part is composed of multicast sources and first-hop routers. This part does not require any multicast signaling protocol. It only needs to send multicast data packets continuously. The source IP address of these IP data packets is the IP address of the multicast source, and their destination IP address is a multicast group IP address. The second part is composed of last-hop routers and group members. The IGMP protocol works in this part. A last-hop router uses IGMP to check whether there are group members and to manage group members. The third part is a network composed of multicast-capable devices, which generally include routers and switches. The PIM protocol to be described today works in this part. What problems can be resolved by multicast routing protocols? How does a first-hop router forward a received route? What enables a network to forward multicast traffic only to links that require the traffic? How can loops be prevented during traffic forwarding? To address these issues, multicast routing provides three key functions, the most important of which is to build a loop-free multicast distribution tree, shown in green in the figure here. First-hop routers distribute the multicast traffic that they receive along this tree. The second function is to check whether packets are received by the correct interfaces, ensuring loop-free forwarding of multicast data. The third function is to create multicast forwarding entries. A multicast router uses a multicast routing table to guide traffic forwarding along multicast routes. This routing table includes entries in the format *G and SG, in which * indicates any source address, G indicates a multicast group address, and S indicates a specific source address. PIM is a multicast routing protocol that uses unicast routing protocols to forward data, but PIM is independent of any specific unicast routing protocol. Reverse path forwarding is an important mechanism used by PIM to check whether packets are received by the correct upstream interfaces. RPF can be implemented through any unicast routing table, such as an OSPF or RIP routing table. This is why PIM is called a protocol-independent multicast protocol. There are three common types of PIM: PIM-DM, PIM-SM, and bidirectional PIM. In this course, we'll focus on PIM-DM and PIM-SM. First, let's take a look at PIM-DM. This mode is used on small-scale networks with densely distributed receivers. PIM-DM assumes that group members exist at each corner of a network and forwards traffic in push mode. In push mode, a device first forwards traffic to all devices on the network segment without considering whether it is required. If no hosts on the network segment require the traffic, this network segment branch is then removed from the SPT. The process of forwarding packets to the entire network is called flooding, and the process of removing unnecessary branches is called pruning. Once all unnecessary branches have been pruned, the network becomes stable, and data is forwarded along the tree. If a branch later requires multicast traffic, the branch is added back to the tree through a process known as grafting. Now, let's turn to the other mode, PIM-SM. This mode is used on networks with large members of sparsely distributed multicast members. PIM-SM forwards traffic in pull mode. This mode assumes that no network segments require the multicast traffic of a group. A network segment needs to send requests if they want the traffic. An important PIM router, called the rendezvous point, is maintained on the network. To join a multicast group, a host sends a join packet to the RP, and *G entries are set up on each device that receives the packet. Then, a rendezvous point tree is created with the RP at the root. The root of a shortest path tree is a multicast source, whereas the root of an RPT is an RP. Next, I'll give a detailed explanation of the PIM-DIM mode. PIM-DIM mainly uses the following types of packets. Hello packets are used to establish and maintain neighbor relationships. Join and prune packets are used to join multicast distribution trees and remove branches from those trees respectively. Graft packets are used to add devices to multicast distribution trees. Graft ACK packets are sent to acknowledge a graft after it is complete. Finally, assert packets are used to ensure that no multiple multicast routers send the same multicast group traffic to a network segment. Directly connected PIM-DIM devices use hello packets to maintain a neighbor relationship. After PIM is activated on the router interface, the interface sends hello packets 224.0.0.13, a multicast address reserved by PIM, and listens for hello packets sent by other devices. In this way, hello packets are used to discover neighbor relationships and negotiate PIM parameters. Other types of multicast packets can be sent and received only after a neighbor relationship is established. You can check whether PIM neighbors have been discovered on a router by using its command line interface. Now, let's move on to the PIM-DIM working mechanisms for flooding, pruning, grafting, and asserting. First, let's look at the flooding process. In the figure shown, the multicast routing function is enabled on the 4 routers, and they are running PIM-DIM. The multicast source 10.1.1.1 starts to send multicast data to the multicast group 239.1.1.1.1. The destination addresses of the multicast data are all 239.1.1.1. After a data packet reaches router A, the first hop router, router A, floods the packet from all interfaces except the interface that received the packet. The routers B, C, and D receive the packet and flood it in the same way. In this way, the multicast packet is spread to the entire network. Multicast routes also have routing entries. A multicast routing entry first has an identifier, and the entry is in the form of SG for SPTs and *G for RPTs. PIM-DIM uses SPTs, so when a router receives multicast data, it creates an SG entry, where S indicates the multicast source and G indicates the multicast group. In this example, the SG entry is 10.1.1.1, 239.1.1.1. A multicast routing entry also contains the two more fields, of which the first is the upstream interface, also referred to as the incoming interface. This is an RPF interface, the interface pointing towards the multicast source. PIM performs an RPF check based on unicast routing entries, searches the unicast routing table for the route to the multicast source, in this case 10.1.1.1, and determines the outbound interface. This outbound interface is the upstream interface in the multicast routing entry. Multicast data is permitted only if received from the correct upstream interface, that is, RPF interface, and discarded otherwise. This ensures that multicast traffic is forwarded in a loop-free manner. The second field is the downstream interface list, also referred to as the outgoing interface list. When a PIM-DIM router receives a multicast data packet from an upstream interface, by default, it forwards the packet from all interfaces except the upstream interface. This is because all these interfaces are present in the downstream interface list. When branch pruning is performed, the pruned interfaces are removed from the downstream interface list. In addition to the PIM routing table, each router maintains a multicast routing table. This routing table can include entries from the independent routing tables maintained by each multicast routing protocol. In this table, we can see the multicast routing entry 10.1.1.1, 239.1.1.1. Continuing with the same scenario, multicast traffic has now been flooded throughout the network. On this network, user terminals are directly connected to routers B and C. Through IGMP, these routers learn that the multicast group 239.1.1.1 has receivers. In this network architecture, routers B and C are last hop routers because they are directly connected to multicast receivers of the group. Both routers B and C needs the multicast traffic. Router D, however, is a leaf router and is not directly connected to any multicast group members. Router D does not need the multicast traffic. Therefore, router D sends a PIM prune packet to the upstream device, requesting to be pruned from the multicast distribution tree. When other routers receive the prune packet, they remove the packet receiving interface on router D from the downstream interface list of the corresponding routing entry. Finally, the SPT is pruned into the tree shown here in green, and multicast traffic travels along this SPT. After network convergence is complete, prune packets do not need to be continuously sent. Now, let's look at the graft process. We know that this branch has been removed in the previous process. Assume that hosts on this branch later join the multicast group, causing the branch to need the traffic of that group. To join the tree again, router D sends a graphed packet to its upstream neighbor. Router A, after receiving the graphed packet, router A responds with a graphed ACK packet. The downstream interface on router D is added to the downstream interface list, and the traffic is sent to the branch again. After the network becomes stable, the multicast distribution tree looks like this. The root of this tree is a multicast source, and each branch tail is the network segment where group members reside. Such an MDT is called a shortest path tree. The prune override mechanism is used in special scenarios. In this scenario, the three routers are connected to the same layer 2 switch, and PIM-DIM is activated on their interfaces. At the beginning, R2 and R3 were both connected to multicast group members and forwarded the multicast traffic sent to those members by R1. Now, the host connected to R2 has left the multicast group. R2 does not need the multicast traffic anymore and sends a prune packet to its upstream neighbor. The three routers are connected to the same switch. When the switch receives the prune packet, it floods the packet to all interfaces except the one on which the packet was received. After receiving the prune packet, R1 immediately sets its GE000 interface to the pruned state and stops sending multicast traffic to the interface. What will be the consequence of this? Yes, R3 fails to receive the multicast traffic though it is still connected to group members. PIM provides the following solution to this issue. If an interface is connected to only one PIM neighbor, it is set to the pruned state immediately after receiving a prune packet. However, if an interface is connected to multiple PIM neighbors, a prune delay timer is started upon receipt of a prune packet. This gives other routers, in this case R3, a short time during which they can override the pruning process. The assert mechanism uses PIM-assert packets. As shown in the preceding figure, R1 and R3 receive multicast data from their RPF interfaces, and they both forward this data. As a result, R4 will receive duplicate multicast data packets. To prevent duplicate data, either R1 or R3 needs to be elected as the forwarding router. The election uses a mechanism known as assert and implemented through assert packets. An assert packet contains source and group addresses, the metric of the unicast route to a source, and the priority of the routing protocol that discovered the route. When R1 or R3 receives the data of the multicast group 10.1.1.1, 224.1.1.1 from its downstream interface GE001 in the group 10.1.1.1, 224.1.1.1, each router will become aware that another multicast router is also forwarding the multicast data of the same group. R1 and R3 will then send a PIM-assert packet. The packet content is shown in the figure here. For this example, let's assume that R1 learns the route to 10.1.1.1/24 through OSPF with the cost being 2, and R3 has a static route to 10.1.1.1/24, with the cost being 0. After receiving the assert packet from the peer, R1 and R3 start the forwarding router election. First, they compare the unicast protocol priorities of the unicast routes to the multicast source. The router using a route with a smaller priority value wins the election. If the unicast route's priorities are the same, they compare the costs of the routes to the source. The router whose route has a lower cost wins the election. If the costs are also the same, they compare the IP addresses of their local interfaces. The router with a higher interface IP address wins the election. In this example, the priority of the route from R1 to 10.1.1.1/24 is 10, which is a higher priority than the route of R3. Therefore, R1 is elected as the forwarding router. GE001 on R1 forwards the data of the unicast group to 10.1.1.1/24, and R3 does not. When this happens, the downstream interface list of R3 is empty, and therefore R3 uses its upstream interface to send a prune packet to R2, requesting to be pruned from the multicast distribution tree. Now, let's see some basic PIM-DIM configurations. To set up PIM-DIM, enable multicast routing on a router, and then enable PIM-DIM on the corresponding interface. Then, check PIM neighbors. Next, let's discuss another PIM mode, PIM-SM. PIM-DIM is suitable for small-scale networks with densely distributed receivers, whereas PIM-SM is ideal for large-scale networks with sparsely distributed receivers. PIM-SM works in pull mode. Initially, a PIM-SM device does not flood multicast traffic to any network branch unless the multicast traffic has been explicitly requested. Before going deeper to PIM-SM, let's talk about an important concept, the rendezvous point. The RP is the root of an RPT and is responsible for forwarding multicast traffic from the source to receivers. In PIM-SM, the traffic sent from a source goes to the RP, which then forwards the traffic along the RPT to downstream devices. If a branch needs the traffic, the multicast router on that branch sends a PIM join packet towards the RP, requesting to be added to the RPT. An RP can forward the multicast traffic of one or more groups simultaneously. However, a multicast group can receive traffic from only one RP at a time. A master or slave switchover can be performed through the dynamic discovery mechanism. The process of mapping a multicast group to an RP is called RP discovery, and it can be performed statically or dynamically. PIM-SM uses several more types of packets than PIM-DIM. These include register packets, which are used by multicast sources to register with RPs. When the first hop router receives multicast traffic from a source, the router sends the traffic to the RP, which then sends the traffic to multicast group members. You might wonder how the first hop router sends the multicast traffic to the RP. Initially, there is no multicast distribution tree on the network. The first hop router must encapsulate multicast packets in register packets and send them to the RP in unicast mode. The RP then decapsulates the packets and sends the multicast packets to downstream devices. Register stop packets are sent by an RP to the first hop router, indicating that a multicast distribution tree has been established between the RP and the router, and the RP does not need unicast packets from the first hop router anymore. Bootstrap packets are used to elect a bootstrap router and send candidate RP summary information. They also contain some parameter information. CRP advertisement packets are used by CRPs to notify the BSR of their existence. The basic working mechanisms of PIM-SM include the process for a last hop router to initiate an RPT join, process for a multicast source to register with an RP, process of establishing an SPT between a multicast source and RP, and process of switching between an RPT and SPT. First, let's go over the process for a last hop router to join an RPT. Unlike PIM-DIM, PIM-SM requires explicit PIM join packets to construct branches of an RPT. In the network topology shown in the figure, all multicast routers run PIM-SM. At the beginning, multicast traffic is not forwarded to any branch of the network. Then, a host on the network segment directly connected to R5 becomes a member of the multicast group 224.1.1.1. The host first expresses its need to join the multicast group 224.1.1.1 by sending an IGMP membership report packet. The last hop router R5 receives the IGMP packet, creates the asterisk 224.1.1.1.1 entry in its multicast routing table, adds the interface that received the IGMP packet to the downstream interface list of the entry, and sends the PIM join packet asterisk 224.1.1.1 to the RP. R5 knows the RP address, which may be the IP address of the loopback interface on the RP shown in the figure, and can learn the root of the address through a unicast routing protocol, such as OSPF. Therefore, R5 uses the unicast routing protocol to determine the upstream PIM neighbor that is closer to the RP. After receiving the PIM join packet from R5, the RP creates an asterisk 224.1.1.1 multicast routing entry and adds the interface that received the packet to the downstream interface list of the entry. The RP starts to forward multicast traffic to the downstream interface if it has received traffic destined for the multicast group 224.1.1.1. If the network segment directly connected to R6 also includes a host that wants to join the multicast group 224.1.1.1, the host sends an IGMP membership report packet to request to join the group. R6 creates a multicast routing entry asterisk 224.1.1.1, adds the interface that received the IGMP packet to the downstream interface list of the entry, and then sends a PIM join packet asterisk 224.1.1.1 to its upstream neighbor R5, requesting to join the RPT. R5 adds the interface that received the join packet from R6 to the downstream interface list of the asterisk 224.1.1.1 entry. Because R5 is already a branch of the RPT, it simply adds the interface to the downstream interface list and forwards the multicast traffic to the interface. In the end, the RPT constructed looks like this. Now, let's see how pruning an RPT works. Let's continue with the preceding scenario. All members on the network segments directly connected to the R6 router have left the group 224.1.1.1. The members send IGMP leave packets to notify other devices of this. After receiving these IGMP packets, R6 learns that no members exist in the group and removes all interfaces from the downstream interface list of the asterisk 224.1.1.1 entry, after which the list becomes empty. R6 then knows that it will not need the traffic of the group 224.1.1.1 anymore, and therefore sends a PIM-prune packet to the upstream interface, requesting to be pruned from the RPT of asterisk 224.1.1.1. After receiving the PIM-prune packet, R5 removes the interface that received the packet from the downstream interface list of the asterisk 224.1.1.1 entry. After the interface is removed, the list still contains at least one interface. Therefore, R5 remains on the RPT, and multicast traffic is still forwarded from the RP to R5. R5 forwards traffic only to network segments that are directly connected to R5 and have multicast members. It does not forward traffic to R6. After hosts on the network segment directly connected to R5 leave the multicast group, R5 finds that the downstream interface list is empty, and therefore sends a prune packet to the upstream interface requesting to be pruned from the RPT. Previously, we talked about issues between an RP and receivers. Now, let's discuss potential issues between a multicast source and an RP. Multicast data can be transmitted from the source to receivers only after all the issues are resolved. At first, no multicast traffic is transmitted on the network. When the source starts to send multicast data to the multicast group 224.1.1.1, the data is first received by the first hop router, R1. R1 then encapsulates the multicast data in a PIM register packet and sends it the RP, whose address it already knows. The PIM register packet is a unicast packet, and its destination is the address of the RP. The PIM register packet containing multicast data is routed to the RP, which decapsulates the packet and obtains the multicast data. The RP then forwards the data along the established RPT, continuously encapsulating multicast data in register packets, and sending these packets to the RP is inefficient and will cause R1 and the RP to be overloaded when multicast traffic is heavy. To resolve this issue, the RP sends an SG PIM join packet for 10.1.1.1, 224.1.1.1 along the route to the source in an attempt to build an SPT between the RP and the source with the source at the root. In this manner, the RP can directly receive multicast data from the source instead of encapsulated unicast packets. The SG PIM join packet is transmitted hop by hop to the source, after which an SPT is established between the RP and the first hop router R1. Multicast traffic is sent to the RP along the SPT, and then the RP sends the traffic to the various branches along the RPT. After the previous step is complete, an SPT is established between R1 and the RP. This means that R1 directly sends multicast traffic to R2, which sends the traffic to the RP along the SPT. However, R1 still sends multicast data to the RP in the form of unicast register packets. As a result, the RP will receive duplicate multicast data, which is unnecessary. In fact, because an SPT has been set up, the RP does not need register packets from R1 anymore. Therefore, the RP sends a PIM register stop packet to R1. After receiving the register stop packet, R1 does not use register packets to send multicast data to the RP anymore. Multicast data is sent to the RP only along the SPT. At this point, the SPT and RPT work as follows. Multicast data is sent from the first hop router R1 to the RP along the SPT, and then forwarded by the RP along the RPT to the downstream branches that need the data. This transmission process is improper. Multicast traffic should be directly forwarded from R2 to R5 without being sent through the RP. This issue can be resolved by performing an SPT switchover. In PIM-SM, by default, the last hop router attempts to set up an SPT with the source immediately after receiving a multicast data packet from the RPT. The last hop router can then obtain the multicast data from the first hop router along the optimal route instead of receiving this data from the RP. The last hop router R6 sends a PIM join packet of 10.1.1.1, 224.1.1.1 to the source immediately after receiving a multicast data packet of the group 224.1.1.1, attempting to set up an SPT. R6 uses the unicast routing table to determine the RPF interface pointing towards the source. An SPT uses multicast source information to perform an RPF check. R2 is the next hop of the route from R5 to 10.1.1.1. Therefore, R5 sends the join packet to R2. After receiving the join packet, R2 adds the interface that received the join packet to the downstream interface list of the multicast entry 10.1.1.1, 224.1.1.1. The current shapes of the trees are shown in the following figure. It is found that R6 will receive 2 copies of the same multicast data, which is meaningless. Since the multicast data can be obtained from the SPT, it is unnecessary to obtain this data from the RPT as well. Therefore, R6 sends an asterisk 224.1.1.1 prune packet to the RP, requesting to be pruned from the RPT. In addition, R5 is on both the SPT and RPT and can obtain multicast data from the source along the SPT. Therefore, R5 sends an sgRPT prune packet to the RP, requesting to be pruned from the RPT. After receiving the prune packet, the RP removes the interface that received the packet from the downstream interface list of the SG entry and sends a prune packet along the route to the source. After receiving the prune packet, R2 removes the interface that received the packet from the downstream interface list of the SG entry. Finally, the shape of the multicast distribution tree is like this. This is the optimal transmission path. Now that we've learned about the basic working mechanisms of PIM, let's move on to another concept in PIM-SM, the designated router. A DR is elected on a multi-access network segment and plays an important role for networks where a multicast source and multicast group members reside. The multicast source and multiple routers are all connected to the same switch. When the source starts to send multicast traffic, both R1 and R2 receive the traffic and sends registration requests to the RP, which is resource-consuming. To resolve this issue, a DR is elected between the interfaces that connect R1 and R2 to the switch. Then, only the elected DR sends a registration request to the RP. The multicast traffic received by the other router is discarded. For each multi-access network, PIM elects a DR using hello packets. The DR row can be preempted. A hello packet carries a DR priority and interface address on the network segment. After receiving a hello packet, each PIM router compares its own DR priority and interface address with those carried in the hello packet. A single DR is then elected to send and receive multicast packets on the multicast source or group member side. In a DR election, the router with the highest DR priority wins. If the DR priorities are the same or one or more routers do not support hello packets carrying DR priorities, the router with the highest IP address wins. If the elected DR fails, the other PIM neighbors trigger a new DR election. The DR connected to a multicast source is called the source DR, and the DR connected to multicast group members is called the receiver DR. That's all for today. Thanks for listening.